Hi, we are a group of fourth year undergraduate students from the Department of Mechanical Engineering, Sandeepan, Pratasha and myself Arijit. The topic of our video presentation is using particle swarm optimization techniques in computational fluid dynamics, CFD. So what is CFD? In CFD, we analyze fluid flow using numerical techniques. In classical CFD, we first write the governing partial differential equations of Navier-Stokes, and then we break the entire system into finite discrete elements. And for each timestamp, we perform the calculations, and then we finally present our simulation. What is PSO? PSO is a computational technique in which we have a set of candidate solutions which traverse through the entire search space. The movement of each particle is dependent on its velocity and position, which in turn are influenced by the locally best solutions and the globally best solutions. For each timestamp, for a particular particle, we perform simple mathematical operations to update its current velocity and position. This is expected to move the entire swarm towards the best solution. Now, what is the motivation behind our presentation? Basically, the classical CFD techniques require considerable user preparation and CPU execution time, whereas our bottom-up nature-inspired technique will be much more efficient and a lot simpler to implement. Because at the end of the day, nature doesn't understand partial differential equations, right? There are three main characteristics of particle sum optimization, the first of which is separation. It stems from the fact that we want particles to avoid and detect collisions with each other. What we do is for each candidate solution, we find its average distance from its neighbors, and then we influence its speed in such a way that it maintains a certain separation from them. The second characteristic is called cohesion. What we also want is to form clusters. So for each particle, we first calculate the average position of its neighborhood local candidate solutions, and then we push the particle towards the center of mass. The last characteristic is called alignment. We also want the entire swarm to move in a particular direction. So what we do is, for each particle, we first calculate the average speed of its locally adjacent candidate solutions, and then we increment the current speed in such a way that it matches it. Now that our model has a realistic swarming behavior, we will remove some conscious actions like cohesion and alignment from the model, and we'll replace it with particle-to-particle interactions governed by physical laws such as the law of thermal conductivity, density, specific heat, and temperature for each particle. And we'll also recalculate the average velocity and position metric for each particle in each timestamp. Uh, Now let's first look at the heat balance equation. For each individual particle, the change in heat balance can occur from one of these 8 sources. The first one, QA, refers to the heat transfer between the particle and the neighboring air. The second one is the heat transfer between the particle and its immediate neighbors. And these 6 other sources are the 6 walls of the cuboidal shaped model in which we are conducting our simulation. So for calculating each of the 8 heat transfer components of the ith timestamp, we'll simply plug in the values of the source and the sink of the I-1th timestamp into the convection equation. Once we accumulate the net heat transfer, we'll simply divide it by the mass times its specific heat capacity and increment it to the old temperature to get the new temperature of our current particle. Now, to update the particle's velocity and position in each timestamp, we'll first need to calculate its acceleration. And to calculate its acceleration, first we'll need to know the net force acting on it. So here is the force balance equation. The main forces acting here are the gravitational forces of Earth, the buoyant forces applied by air, and the net air resistance. Now once we have the force, we'll calculate the acceleration and then update its old velocity.
Let us start with our simulation experiments. First, we have the swarming simulation experiment. This is useful for simulating the interaction of agents, social or biological, and their emergent collective behavior. The swarming simulation starts with the particles lined up along the base of the left and right wall ready to be deployed in the simulation. We can see this in the first figure. These particles are launched 64 at a time on keyboard key down command so that multiples of 64 particles can be deployed in each simulation. Soon after the particles are launched into the room, collective behavior is developed and a swarm emerges as a result of local rules on the particle level. This is seen in the third figure. The swarm subsequently explores the space driven by its collective behavior. Swarming particles are equipped with trails proportional to their speed to help with the observation of movement. When two vertical cylinders are inserted as obstacles into the room, the swarm reacts to these obstacles, breaking before them and rejoining after them. This can be seen in the last figure. The images of swarm behavior simulation shown here were taken during a period of less than a minute, and the simulation continued afterwards without set time limits. Next, we have our CFD experiments. In these experiments, the particles and the room walls, floor and ceiling are color coded according to their respective temperatures. This temperature ranges from 0 degrees Celsius to 25 degrees Celsius. In this simulation, the subconscious swarming rule of separation is kept and conscious rules of cohesion and alignment are replaced with CFD calculations on a particle level. The room surface and air temperatures are preset in the model and kept constant throughout the simulation, and the air particle temperatures are calculated at each time step as specified in the method section. At the start of simulation, the particles are lined up along the base of the left and right wall. This is seen in the first figure. Subsequently, a set of 128 particles is launched into the room. They quickly form a flow pattern where particles receive heat from the warm floor. As particles rise, driven by the buoyancy force, their temperature changes through heat transfer with other particles and walls. When they reach the cold ceiling, they lose heat, buoyancy force becomes weaker than gravity, and particles start a downward movement. This flow pattern persists if no other interventions are taken in the model. An intervention that changes the flow pattern is the opening of the roof hatch. In the last figure, the roof hatch is opened. As it is opened, the particles rapidly start escaping from the room, propelled by the buoyancy caused by the difference of densities between the warm inside air and the cold outside environment. On leaving the room, the temperature of each particle drops due to exposure to the cooler outside air. The entire simulation from figure 8 through to figure 12 was completed in less than a minute, and the process continued until the simulation was terminated manually.
So now coming to the discussion and analysis of the result of the simulation experiments. So as a starting point, a swarm particle model was created using the rules of separation, cohesion and alignment as it was mentioned before. So after the swarm model exhibited realistic behavior, the cohesion and the alignment rules which had been considered to be applied consciously by the swarming agent, they were eliminated and replaced by the CFD rules underpinned by heat transfer and Newtonian physics. Before the first CFD simulation was carried out, it was expected that the model would exhibit clear and continuous pattern formula akin to the static patterns, as observed in the conventional CFD tools. However, much more complex dynamic behavior occurred. The particle exhibited Brownian motion colliding with each other and with boundaries, while gaining heat from warm surfaces and losing heat to the cold ones. So as expected, the particles were rising when they gained sufficient amount of heat, and they were falling out when the heat was lost. Now, the paper which we implemented does not claim the proof of the model concept fully represents the air movement, but they claim that these results show that reality could be far more complex that represented by the conventional CFD tool. The conventional CFD tool, which has been microflow and IES virtual environment that were used by the paper, it produced detailed distribution in the room volume for a single point in time within the simulation year. And the results were static and it took around 25 minutes of simulation time. Whereas in comparison, the swarming CFD simulation, it was almost instant within a few seconds and it produced dynamic results. However, these results did not include the entire volume of the room, as a particle moves around the room while driven by real-time heat gains and heat losses. So basically, this shows that this showed the need of further development for the swarming CFD is required to cover the entire volume of internal spaces. And it is not a simple matter of adding more particle, but it would require changes in the model that reduce the impact of color rendering of the speed of the simulation, as well as introduction to simplified shapes that would render faster than the currently used cones. But it would still indicate the direction of the particle movement. Also, validation of the new CFD tools is normally carried out using previous software tools, but the swarming CFD is significantly different from the existing tool. So its validation found in the standard simulation software will therefore need to be carried out in an analog facility such as the wind tunnel or using full-scale testing. Now coming to the conclusion. So here we have shown an initial research into the modeling of CFD with swarm behavior. Clear and near static flow pattern formation was expected before the simulation experiment were conducted. However, this experiment, that flow pattern showed that the flow pattern was dynamic with a high degree of Brownian movement in addition to the heat driven flow. A comparison between the swarming CFD and the traditional approach showed the formation of dynamic pattern that occurred within seconds from the start in case of the swarming CFD. Whereas in case of the traditional CFD, it took 25 minutes of CPU time to create a static pattern. Considering that the standard simulation tools use Navier-Stokes equation, which describe the system as a whole from the top down, and which have solutions only for the simplified cases, a question of trust into outputs can be legitimately asked. The swarming CFD requires improvements in the speed of rendering. For instance, the cones used in the current model take longer to render than some simpler shapes such as cube. Finding the shapes that are computationally less intensive to render but still indicate the movement of the direction of the particles would make this work faster, and we can also use a much more number of particles for the experiments. These improvements will help the create representation of air movements in the entire room volume, and that we can follow up by experimental validation process in a wind tunnel or full scale testing. Finally, although this approach requires further development, a proof of concept can be made that swarming particles can be used as a starting point for the bottom-up modeling of the CFD. Hope you enjoyed this video. Thank you.